Welcome to lecture 15. Today I will just summarize some of the concepts that we have done so far and prepare ground for the future. Right. So, we started with the notion of environments. We decided that environments are some variable value bindings for an expression language, for an ML like expression language with declarations. Then we also looked at some possibilities for reversible changes in environments. We discussed environment updation and we also looked at how these environment updations are always of a reversible nature. For example, in the expression language with a let construct, as in ML, you are evaluating an expression in some original environment rho, and if there is a declaration inside it, what it means is that you temporarily update the environment to a new little environment. The processing of the declaration gives you a new little environment in which you evaluate this expression, but eventually you revert back to the original environment, and these changes are reversible. On the other hand, while looking at a simple imperative language, we first took a simple view of what it means for we defined an abstract concept of a state, and we defined that also as just variable value bindings, and we defined the semantics using this state transformation as an updation mechanism with, of course, and we were of course interested in modeling state changes. So, we have a state updation notion which looks a lot like the environment updation notion, but is actually quite different because it leads to irreversible changes. So, we also defined the semantics of commands with an underlying expression language in which, for example, this is a permanent state change. Wherever you have an assignment statement, there is a possibility of an irreversible state change. We discussed the various control structures, the most elementary control structures, namely sequential composition. We gave an inductive definition for that, and always when we are talking about commands, we are talking about the possibility of state change, and other control structures like the conditional control structure and the looping control structure, right. So, and of course, in our general discussion on transition systems, we also had to keep certain things in mind in general, which is independent of programming languages. These are some general questions like when can configurations get stuck, and that is something that you might require to know even while modeling other systems which are not necessarily programming language based. Okay. In the particular case of formal languages, by formal languages I mean programming languages, and specification languages may be any language which has a formal grammar, which can be completely defined by a grammar. Are these definitions inductive? So, if your definitions are all inductive, then you have a certain level of confidence that that most of your configurations will not be stuck, because then you can use the induction process to prove that some of your non-terminal configurations are not stuck. So, but there could be stuck configurations even if all their definitions are inductive, and this is something we have seen. This is in programming languages, what it usually means is that this would lead to some form of runtime error, not compile time, runtime error. So, a typical example is in our definitions, for example, we have not explicitly considered various binary operations. We have just considered a general binary operation, but if you were to take something like division as a binary operation, then the axiom, the corresponding axiom for division would have to include a side condition that you are never dividing by 0. And so what that means is that there are configurations in which you might be dividing, in which an expression might contain a division by 0 which would be stuck, for which you will not be able to apply those axioms or rules of inference, right. Okay. So the way we have defined things so far is that provided all our expressions are total functions, by total functions it means that they are not undefined for any particular value of the arguments, then you can show that no non-terminal configuration ever gets stuck. And another thing you can show is that the execution of while programs is deterministic. So far we are looking only at deterministic programming languages. In fact, we will never actually look at non-deterministic programming languages, but it is important for us to know that deterministic in this case means that our transition relation is really a function, which it need not have been to start with, right. And a powerful proof technique for proving properties about programs is an induction method. Also, one obligation is that you have to also define what is meant by a behavior, and we defined the behavior of expressions in terms of an evaluation. So if an expression in the imperative language, if in a given state the expression can evaluate to some terminal configuration, then the value in that terminal configuration is taken to be the result of evaluating this expression in that state. In general, as I said, since we are not assured that the transition relation is a function, in general this means that you could have more than one possible result for the same expression in the same state. However, once you have proved that your transition system for the language is deterministic, the result of this would be a singleton set, right. Sometimes non-empty, of course, sometimes empty, of course, but that is when you consider more complicated cases where evaluation itself could be, where the expression could be recursive and therefore there could be an infinite recursion, or the expression could be could have commands embedded in which there are infinite while loops, etc. Then similarly for Boolean expressions we defined the notion of evaluation, and for commands we defined the notion of an execution, and commands yield states, and since our transition relation is deterministic, what it means is that every command defines a function from state to state. So from an input state to an output state, and what it also means is that it also confirms the view that commands are state transformers. Okay. Having defined the notion of a behavior, we defined program equivalence. Well, two expressions are equivalent if and only if under all states or under all environments they yield the same results. This of course has to be taken with a pinch of salt. Two commands are equivalent, or two programs are equivalent if and only if under all input states their executions yield identical final states. We also looked at the futility of actually trying to give a definition for equivalences of declarations, and well, I said it's a weak definition, but we'll live with it for some time. Okay, then our main problem was that we had defined the state as we have defined the state as an association between identifiers and values in our while programming language, and then that brings up various other questions. When you actually want to extend the language to other constructs, then it turns out that you have for example, the assignment is the most important form of an imperative command, a state changing command, and all other commands which change state in visible or invisible fashions can be modeled in terms of sequences of assignment statements. So this is a common practice. So the assignment statement is very important, and what it turns out is that our notion of state is rather weak, because firstly, the left hand side of an assignment is not necessarily always just an identifier, it could be an expression. Secondly, identifiers are redeclared, and there is an irreversibility. There is a reversible process also when you consider scope issues, lifetimes of identifiers and so on. And so redeclared identifiers means that they are actually two different identifiers carrying the same name, and then there are issues like scope, lifetime, extent, which so with a simplistic notion like a state, it's not really possible to capture that. Also, the notion of side effects and what happens in side effects is also quite difficult to capture in the case of states, because of the fact that many different objects might actually have the same name, but the same object could also have many different names due to aliasing, and therefore when you have aliasing, when the same object has many different names, then what you have as side effects are essentially invisible assignments. I mean, you make an assignment to one name of that object, but that means that you also simultaneously made assignments to all other names of that object too. So there are all kinds of invisible effects which complicate matters. So in general, when you look at the assignment statement, you might have complicated expressions, and also there is a restricted language. I mean, not all source expressions are meaningful, not all target expressions are meaningful. The set of meaningful source expressions is not disjoint from the set of target expressions. There are anonymous target expressions, there are anonymous objects which are created, which do not have, I mean, and names keep getting transferred as new objects are created, and old objects lose their names. And so what it all boils down to is, when you have anything like an assignment statement in a programming language, then there is an implicit part of that assignment is that there is some need for a new entity called locations, which somehow look like, which somehow is a model of memory in most digital computers. In fact, so if you look at all these problems, what happens is that it's necessary to identify this notion of this object, and we have object creation in several different ways, temporary or permanent, and we have updation of its values. So we require something in between an identifier and a value, and that is, and for that we require the existence of a new domain of objects called locations, which always are new. Whenever a new object is created, it has a new location, and the new location has a contents, right. So, and this is particularly when you have anonymous objects, and especially names changing from one object to another during the process of the creation of new objects, we require to be able to locate the old object too, even though it has lost its name. And so in this process what it means is that our notion of a state, which was very close to the notion of an environment, really has to undergo some drastic revisions, right. So, and firstly we require to be able to model irreversible changes, and we have to be able to distinguish between environments and a set of objects which have which are distinguished by this process. And so we will look at locations as somewhere intermediate between identifiers and values. So, and then our declarations in our imperative language automatically take a certain meaning. So, constant declarations would just be treated like the variables of ML. So, they would just be identifier value bindings, whereas variable declarations would actually be identifier location bindings. So, during program execution you could have new names, you could have the same name transferred to several objects, but all those objects would have different locations. Yeah. So, so at least you would be able to look at locations somehow as identifying the basic structure of an object during execution. So we'll define variables as identifier location bindings, and of course we'll define locations as associations between so we'll define locations as containing values. So there is also a location value association, which is not really a binding. The word binding is normally used for declarations and so on and so forth. So, and we will, another thing is that we will look upon as the targets of assignments only as locations, and the sources of assignments as the values contained in locations, right. So you can think of a location as containing a value which can be changed during command execution, but during the lifetime of this location there is an identifier to location binding which comes from a declaration, right. So you can have fairly ephemeral creations like that. So we will assume that new locations are always created by declarations. Every location has a lifetime or an extent, okay, which usually lasts till that location is explicitly or implicitly disposed of. So the fact that a location is created by a declaration means that it does not necessarily last forever, because a declaration creates a little environment which has a lifetime which is usually governed by the scope of that declaration, right. So you can, so we can have what constitutes scope in a program text works out at runtime to a lifetime for each object that is created in that scope. So each object that a declaration has is created when that declaration is elaborated, and it has a lifetime which lasts till the end of that scope, and at the end of that scope it is automatically disposed of. Of course, it is possible in the case of, for example, pointer based creations, to dynamically create new objects, new locations which are created with typical statements like new p, for example, and which get disposed of also explicitly. So the creation of, so locations might be created either through declarations or through commands, and they might be disposed of either because of and they have a finite lifetime which might depend upon whether they are explicitly or implicitly disposed of. right. So and when they are implicitly disposed of, we are usually talking about a reversible change, and when they are explicitly disposed of, we are talking about an irreversible change. So we will assume that instead of assuming that we have an unlimited number of identifiers which can always be used, because of the problems associated with having the same identifier for several different objects and the same object having several different identifiers, we will assume that what we have as unbounded is really a number of locations. So every time a location is created, there is no conflict between that location and anything else that has been created before and which still is living, which is not dead. In fact, we will go further and say that every time we create a location, we create a brand new location which has nothing to do with any location that was created in the past or even died in the past, which is something we really cannot say for identifiers. Yeah. So locations actually take that take the role of an unbounded number of identifiers that we had in the state. So a refinement of the concept of state is that you assume at any stage that you have only a bounded number of identifiers, but because your declarations, when you elaborate declarations, you get only a bounded number of identifiers, you require only a bounded number of identifiers. However, because of the fact that you might be dynamically creating new objects to which you might bind the existing bounded number of identifiers, what you require really are an unbounded number of locations. In practical terms, what it means is that you are really assuming that you have got an unbounded amount of memory in modeling the language, in modeling the semantics of the language, which is not completely realistic, but it is an ideal which can be refined later when you define an implementation document with limits imposed on those things, right. So it's the rest of it, when you actually have a finite memory and you have to model the language, then it is a matter of doing a certain amount of exception handling. Otherwise, in an ideal environment, you assume that you have a computational environment in which you have an unbounded number of resources, but you have only at any stage in the computation you have only a finite number of identifiers to deal with, right. So these locations can contain, of course, varying values during their lifetime. So we will define a store as just a finite set of location to value associations. We will not use the word bindings there, because when we are talking about these associations, we are talking about associations which can change, and this concept is not very surprising, or it is almost an inevitable consequence of having an imperative model of computation. So it really depends upon the model of computation that you possess, that you are trying to that you are trying to deal that you are really trying to deal with, and any kind of imperative model of computation in which states can be updated irreversibly, in which there are objects which can be updated irreversibly, brings in almost the concept of locations, right. So right, so we will look upon environments as being created by declarations, and in particular we will look upon constant declarations as identifier value associations with no locations in between, and we will look upon variables as identifier location bindings, and stores, which are a refinement of the state concept, would just be location value assignments, right. So we might think of the important problem with the assignment is that the left hand side of an assignment is really a target. The target of an assignment is as I said, is a possible collection of expressions restricted class of expressions, and the sources of assignments are also restricted classes of assignments. But the important distinction we will make is that the sources are all values and the targets are all locations, and these are called L values and R values, right. And once you bring in the notion of stores, and since you are almost so there is a concept of what can constitute a storable value. That means what kinds of values can you put in locations, right. So we will look upon storable values for the present. Yeah, we will look upon storable values. Firstly, you could have constants in them. You could have you could also have locations themselves as storable values, right. And lastly, because of the von Neumann sort of an architecture that is an implicit underlying architecture of all imperative languages, what happens is that your storable values could also be programs. In fact, this is the only way you can account for self modifying programs. Have you heard of self modifying programs? So a typical example are the S expressions of Lisp. Yeah, so what it usually means is that in practical terms it is actually very simple. You have a piece of code which actually accesses itself and modifies it and then executes it. But logically you are looking at it as a problem of a function or a program being applied to itself, and function application to itself is logically unsound, right. However, with the notion of locations and storable values, these things can be given a meaningful interpretation without actually getting into any contradictions. So I mean it's mathematically unsound to think of a function f being applied to itself, but if you look at some of these self modifying programs written in Lisp or even assembly language, after all you can load the entire assembly program in starting from some location, and you can actually access that location and modify things if you like, and then transfer control to execute the modified code. While it seems practically quite feasible, if your transition system has a transition relation which is actually a function, then all this is tantamount to a function being applied to itself. A function has a certain type, but how can you actually apply it to either itself or to a modified form which in which the types are. That means if your function was originally defined as going from some domain D to another domain D prime, this kind of application means that for such an application you are actually, this function also has the type that it can go from D arrow D prime to D arrow D prime, which seems quite ridiculous. So there are all these contradictions which is something that mathematicians completely avoid, but somehow which seem to make programming sense, because we know it can be done and we know it is possible. So it turns out that once you introduce locations, you can actually look upon locations as being distinct from identifiers, and you can give types, you can assign types to locations and to identifiers in such a way that such functions become meaningful if you provide a suitable mathematical structure. Anyway, so we will not go into that. It is enough for us to know that for any consistent theory which requires an explanation of all the kinds of different forms of object creation that we have seen, it is necessary to have something like locations and stores, right. So, part of our storable values would also be, for example, when we do procedures, we will also define procedures as being storable values, just like they can be, just like programs could be storable values, right. And that is in fact the only way to explain transfers of control to procedures and to define the effect of procedures on certain values and the returning of certain values. Yeah. Okay. So, I will stop here today and we will continue next week.